we'll move to the third part, which is receptor reserve, and all three of these together are going to tell us something about what we call the efficacy of the drug. But receptor reserve, which is also called spare receptors, awful term. This is not what we're talking about. So this is a spare tire. You got a regular tire and a spare tire. And we know what a spare tire is. A spare tire is the tire that you, even before they had these rinky-dink little tires, when I started driving, spare tires were still tires that you didn't really like. Spare tire was barely a tire that sort of held air, and you could drive someplace with it, but you really didn't want to stay on that tire forever. It was a tire of a different sort. A spare tire in today's car is clearly a tire of a different sort. No further than 50 miles an hour. I don't think that's the standard for most tires. But they call them spare receptors, and people think, oh, well, they're like extra. They're sort of a backup. They're sort of out there in case you need them, in a case of emergency. That's not the way to think of spare receptors. So for cars, spare tires are not normal. There is no such thing as a true spare receptor. Oh, we got a bunch of good beta receptors. I'm a spare in case they need me, in case one had to blow out. Maybe they can finish and get all the way home on their jog because they need another beta receptor. No, that's not it at all. They're not spare receptors. What is really different about the system is that some systems run out of signal transduction molecules and pathway after you reach a certain level of activation. So remember, we said, for example, norepinephrine, activating a beta-1 receptor in the SA node of the heart. That beta receptor is a G protein coupled receptor, makes the GTP alpha thing, that splits off and goes over to adenylate cyclase, and it makes the cyclic AMP. Well, if that system is lacking and runs out basically, you can continue to activate the beta receptor, but if there's no capacity to stimulate adenylate cyclase anymore, what good is it? That's extraneous above above any useful level of beta receptor activation. So theoretically, and it's not just GPCRs, this could happen in a lot of different kinds of receptors, but you can activate a receptor, you can, bind a receptor, have affinity for it, you can have efficacy to try to drive that receptor, but if the signal transduction system is done, what's going to happen is you're not going to get any more bang for additional receptor occupation and activation. Now, when this term was sort of developed, people said those are spare receptors. Well, the reality, it's not the receptor probably that's sort of changing. What really is changing is the transduction mechanism is running out of gas. So that's why I say spare receptors is a misnomer. It's an adjective modifying the wrong thing. The receptors are just ordinary receptors. But what happens in some instances is that you can get a maximal effect without activating all the receptors, because your maximal effect is going to be determined by ultimately how much signal transduction you can generate. So remember, bind the receptor, that's affinity. Activate the receptor, if it's an agonist, a full agonist, that's your intrinsic activity. If you do that to a point where you've used up all your signal transduction, more ligand can bind to the receptor and can try to activate the receptor, but it's not going to have a consequence inside the cell. And again, that's called spare receptors, which is not the right way to describe it. A receptor reserve would probably be more accurately described as some kind of limitation downstream from the receptors, maybe like you're maxing out the signal transduction process. Now, there's not good quantitation on a lot of this. So this is sort of in hypothetical kind of stuff and at one level. Yeah, question?
So spare receptors, do they not have an effect since you've already reached your maximum?
You use the word spare receptors, I'll let you do that. But yeah, that was his question is, so activation of spare receptors doesn't have an effect because you've already used your maximum transduction mechanisms. Exactly. But they're not really spare receptors in the sense that, well, they're there in case you need them and they're different from other. They're ordinary receptors. It's just in some situations, you only need to activate fully maybe 10% or 50% of the receptors in order to get the maximum response. Those remaining receptors are identified as spare, although what's really, the description would be limitations in the intracellular surface or in the rest of the transduction process. Yeah, question?
Here you are talking about a receptor, you're not talking about the concept? I thought it was just
I'm not talking about, there are specific examples I'm not going to give you. I mean, there are some specific examples, but we're not going to bore you with those. It's really the concept that we know they exist in some situations. So what we're trying to get at, again, we're trying to get from a drug out there in your body to an effect. And first we say it has to have affinity for the receptor. And that we can quantify, no arguments about it, that's your KD value. That's your concentration of the drug required to occupy half of the receptors. Now we also have to consider the fact that some drugs will activate the receptor, move it to the active form conformation. Some drugs may, and those are full agonists. Some drugs may move it to the inactive conformation. Those are full inverse agonists. Some may not change the conformation, although they bind. Those are the antagonists. We got the partials. That's another factor to consider when we think about what's the drug going to do for you. And the third thing is, maybe that receptor system has what are called, inappropriately called, spares. And so in some situations, you can get a maximum effect by only occupying 50% of the receptors, for example. And those extra receptors don't matter much. But here's the question, because they do matter in some situations. Where's the situation where having an additional 50% of receptors, let's say we've got a system that has 50% of what they'd call spare receptors. And in the case of a full agonist, those 50% of those receptors are wasted because once you get beyond the full signal transduction by activating half of those receptors, you don't need the rest of them. But where's the situation where you could get a bigger bang if you had spare receptors?
Have like a competitive inhibitor or something like inverse.
If you have a competitive inhibitor, or the classic example is a partial agonist. Let's do just one drug at a time. We could combine drugs and we'll get there too. But the classic example is if you have a partial agonist, let's say there's a drug that has intrinsic activity of 0.5. It's a partial agonist. It can only convert about half the receptors to the active state. But if there are twice as many receptors as would be necessary for a full agonist, that partial agonist can bind all of them and activate all of them at a half level, and that will get you a bigger bang. So in the case of spare receptors, a partial agonist, a drug that has an intrinsic activity of less than 1, let's say it's 0.5, can in some situations give you as big an effect as a full agonist. It's not because it has a different intrinsic activity. It's not because its intrinsic activity has changed. The partial agonist for each receptor interaction will produce about half maximum effect. But if it has twice as many receptors that it can bind to because they're so-called spares, now you can get that full effect with a partial agonist. That make sense? Simpler than yours. We'll get to yours on Monday when we do combination kinds of things. But the point is, they're called spare receptors. They're not different, though. They're not less than normal receptors. They're not the ones that you sort of wait till the very end kind of thing. They're just out there. It really would be better described as sort of a limitation at some point after the receptor. Let's see, I think we had just walked through this. The situation, sometimes the number of receptors occupied doesn't determine the maximum effect. Sometimes there are some additional receptors, and when you have a partial agonist in the presence of these so-called spare receptors, you can get a bigger effect of the partial agonist. Again, I'd call it receptor, I wouldn't call it receptor, a spare receptor, you might call it receptor excess, because it's more receptors than is needed for a full agonist. Question? Yes, yeah, the big thing that happens in the case of spare receptors is all of a sudden a partial agonist can give you a bigger maximal effect. a partial agonist can approximate or even reach the maximal effect of a full agonist if they're what they call spare receptors, or if you want to call it a receptor excess, that kind of a thing.
They don't help with full.
Full agonist, once it's occupied, if it's 50% spares, once it's occupied 50% of the receptors, you can occupy another 20% and you're not going to get a bigger effect because that's not limiting the response. The response is being limited below the receptor. So we call that receptor reserve. Previous one. Somewhere there's a good graph of this, but essentially we'll get to this in a second. So we get receptor reserve is the spare receptors. So three things we've talked about. The first two are really drug receptor specific kind of properties. Affinity, and we're going to measure that. We're going to give you a KD, it'll be so many micromolar, and we're going to compare all kinds of drugs with KDs for the same receptor. We're going to look at the same drug at KDs at different receptors to show selectivity of the drug, potential value there. That's a really hands-on kind of a number. Intrinsic activity, arbitrary scale from 1 for a full agonist, 0 to an antagonist, -1 to a full inverse agonist. That's going to impact what the drug does as well. And lastly, receptor reserve. In the case of receptor reserve, or excess receptors, or whatever you're going to call it, something that has intrinsic activity less than 1 can can enhance its intrinsic activity if there are more receptors available, if there are spare receptors available. And so all those are going to come together for efficacy. Efficacy is simply the effect that you get when you give that drug. It's dependent upon affinity, which is binding to the receptor. It's dependent on intrinsic activity, which is the ability to activate or turn off, or just simply bind in a neutral way that receptor. It's related to whether or not there are spare receptors in that system. Intrinsic activity is a unique drug-receptor interaction. Each drug will have an intrinsic activity for that within that receptor when it binds. Affinity is a drug-receptor specific kind of a thing. Spare receptors has got nothing to do with a particular drug. That's a physiology issue. But the outcome is different if there are spare receptors versus not spare receptors when the intrinsic activity is less than 1. So the affinity, intrinsic activity, and efficacy are all going to come together here. The efficacy of an agonist is a measure of how efficiently it stimulates the receptor to produce the effect. An agonist is a higher efficacy when it produces a bigger effect, and lower efficacy when it produces a smaller effect, obviously.